Hello, hope you're ready for your next calc video. I know I am, but when am I not ready for calculus? Never. Okay, we are on day 116. And today's video is going to be much shorter than yesterday's, but you can title it More L'Hôpital's Room. Okay, I'm going to start with one more warm-up question with the bacteria and growth and decay. And you'll only need your own paper for notes today, so hopefully you've just got your sheets out. Okay, here we go. The number of bacteria call it Y, in an experiment increases at a rate proportional to the amount present. There are 100 bacteria at the start of the experiment. And after 2 hours, there are 150 bacteria. Okay, part A. How many bacteria are there after 5 hours? All right, now if you want to try these questions on your own, I'm going to have 3 parts to them. You can always pause the video and give it a shot and then start it again. So if you'd like to do that, pause now, see if you can figure out part A, and then I'll show you the answers. But, excuse me, if you're ready to see the answers, here we go. Okay, remember, we're always looking for these words. Increases at a rate proportional to the amount present. I want to keep connecting that back to the calculus behind it all. That means the rate present, we'll say y is the amount present, so dy dt equals a rate, k, proportional to the amount present, which would be y. And we know that allows us to use the equation y equals a e to the kt, because that's the solution to that differentiable equation. Okay, so what do I know? I know that after 2 hours there's 150, and initially there's 100. So I should be able to set up 150 equals 100 e to the k times 2, like that. We're going to solve for k. Always a two-step problem. So divide by 100. I would have 1.5 equals e to the k times 2. I would take the ln of both sides. Ln of 1.5 equals k times 2. Divide by 2, we're going to get k is ln of 1.5 over 2. Okay, so knowing that, I can make my equation y equals 100 e to the ln of 1.5 over 2t. And I want specifically how many are there after 5 hours. So now I'm just going to plug 5 in for t. So y equals 100 e to the ln of 1.5 over 2 to 5 times 5. Grab my handy calculator over here. And it's a little bit easier for you with the new version of the calculator because yours all go up in the exponent, but I can type in ln of 1.5 divided by 2 times 5. As long as you have an old calculator, make sure the parentheses keep that whole thing in the exponent. And we should get about 275.568 bacteria. Okay, so as I keep saying, that's pre-calc. No calculus there other than the theory behind it. Okay, let's ready to move on to part B. Here we go. Part B. When will there be 400 bacteria present? Okay, really another pre-calc question. If you want to try to solve it on your own, pause it again and press play when you're ready to see if you've got the right answer. If you're ready to see the answer, here we go. I'm going to start from this formula that we developed with the k value that we got and just plug 400 in for y. So it'll look like 400 equals 100 e to the ln of 0.5 over 2 t. We're solving for t. So what would I do first? Right, divide by 100. You have 4 equals e to the ln of 0.5 over 2 times t. Then what? Take the ln. Ln of 4 equals ln of 0.5 over 2 times t. We want to solve for t. So you can divide by this whole big chunk as long as you are careful with your parentheses, or if you have a new calculator, you use alpha y equals when you divide by that. Or I can say multiply it by 2, so 2 ln of 4. Then it would just be ln of 0.5 t on this side left, and divide by ln of 0.5 to get t alone. And that's just a little bit easier to type into an old calculator because then you don't have to use parentheses. And if you use your new calculator, you don't have to use alpha y equals if you do it that way. Okay, what happened? Ln of 2, oh, I lost the 1.5. Sorry, that was a 1.5 up there. Stop groaning, you're fine. So that should be a 1.5, a 1.5, a 1.5, and a 1.5. So it's really going to be 2 ln 4 divided by ln of 1.5. That looks better. 6.838 hours. Good? Okay, last part. At what rate is the population increasing at 2 hours? All right, again, if you'd like to try it on your own, give it a pause. And when you're ready to see the answer, press play. And here we go. Okay, so like we've seen in the past couple days, when you see the word rate, what does that mean in calculus? Usually it means derivative, and it does. You can take the derivative of that equation, plug in the time you're looking for, and get your answer. Unfortunately, I'm not given a time we want what is the population changing at 2 hours. Oh, just kidding. I am totally given the time. So I'd be plugging that in for 2 if I took the derivative of that equation, which is a great way to do it. Maybe the faster way is to remember that the other rate equation we have for these type of problems is dy over dt equals k times y. So if I want to find the rate, dy dt, I just have to plug in k, which was ln of 1.5 over 2, times y. Now y isn't 2, y is the amount at time 2. So when t equals 2, what amount did we have? Let's see if we have that information somewhere. Oh, there it is. At 2 hours, there's 150 bacteria. So y is 150, so it's 150 you would need to plug in here. And then just go to your calculator and say ln of 1.5 divided by 2 times 150. And the rate is 30.410 if you round it. Bacteria per hour. Okay, so that is one more rate question, exponential growth question. And other than that, I have 1 page of notes on L'Hopital's rule again. So I'm going to switch to a new page if you want to too. Here I go. So recall L'Hopital's rule. If the limit as x goes to a of f of x over g of x is indeterminate, then the limit as x goes to a of f of x over g of x is equal to f prime of x, taking the derivative of the top, over g prime of x evaluated at x equals a. Or in other words, it's equal to f prime of a over g prime of a. And remember, if that answer comes out indeterminate as well, we can take the derivative again. We can keep doing this process until we get a non-indeterminate answer. Okay, let's talk a little bit about indeterminate. What's the most common indeterminate form we see? 0 over 0, right? So that's the one that comes up most often. What are the other ones? Well, if you get infinity over infinity, you saw one of those in yesterday's notes, the one where we really found the horizontal asymptote. Or if you have infinity times 0. We haven't seen anything that come up like that yet. But those are the 3 indeterminate forms. So remember, there's some forms that aren't indeterminate, that sometimes people confuse with those. So things that aren't indeterminate. If we have 0 over plus or minus infinity, or if we have a number, like 5, a constant, 5, 10, whatever, over plus or minus infinity, or if we have 0 over a number, like 0 over 5 or 0 over 20, whatever, what would those limits be? Those limits would always come out to be 0. So not indeterminate, we wouldn't use L'Hopital. And you know, especially with this last one, if I get like 0 over 5, the answer is 0. This one I think we do a lot too. If I have like 5 over infinity, well, constant over huge goes to 0. This one's maybe a little less common, but if the top comes out to be 0, pretty much no matter what the bottom is, as long as it's not undefined, does not exist, would be 0. Also, if you have plus or minus infinity over 0, or if you have plus or minus infinity over a number, or if you have a number over 0, what would those limits be? Because they're not indeterminate. Again, maybe the last one's the most common. If I have like 5 over 0, that probably means I'm at a vertical asymptote, so I'm either shooting up or shooting down forever. So the limit would be plus or minus infinity in all those cases. Okay, so again, the only 3 indeterminate forms when we actually use L'Hopital are these ones in red up here. Every other incarnation of it has a limit that we can say right away. Okay, I've just got 3 examples today, and then we're done. You can get right to doing the homework. I know you're pumped. Okay, first one. Limit as x goes to pi over 2 of tan x all over 1 plus tan x. Okay, what do I do? Okay, well, the ones I show you today are going to be a little bit different than yesterday. Not too different, but a little bit. What's tangent of pi over 2? Picture the tangent graph. The tangent graph's the one that starts at 0, but then what happens at pi over 2? There's an asymptote. So that means tangent of pi over 2 is undefined. So that's annoying. None of these, infinity doesn't mean undefined. So what do I do? Well, we can cheat a little bit. And we know all students love cheating. We can say the limit as x goes to pi over 2, something that's equivalent to tangent. 1 over cotangent. So 1 over cotangent of x all over 1 plus 1 over cotangent of x. Now what? Well, that's just a complex fraction. So what can I multiply everything by, top and bottom by, to make it not a complex fraction? Cotangent. So the top gets a cotangent, 1 gets a cotangent, 1 over cotangent gets cotangent. So I'm going to end up with 1 on top, all over cotangent of x plus 1 on the bottom, like that. Okay, now plug in pi over 2. What's the cotangent of pi over 2? Well, if this is the tangent graph, and tangent of pi over 2 was undefined, it's undefined because when you use the unit circle, you get 1 over 0. So cotangent, when I flip it, it's going to be 0 over 1, which is 0. So this is going to become 1 over 0 plus 1, which is 1. That's my answer. Notice, did I use L'Hopital at all? Nope. This was not L'Hopital. Didn't have the indeterminate form. I had to use a little trig substitution. Got my answer without it. Everything is not going to be L'Hopital, so be careful. Okay, number 2. Limit as x goes to 0 of x over x minus 5 radical x. What do I do first? Plug that 0 in. So we're clearly going to have 0 on top, and 0 minus 5 radical 0. That's 0 minus 0, so we do have 0 over 0, so what's that mean? Indeterminate. Let's L'Hopital this. So this is going to equal, oops, let me get rid of that. This is going to equal the derivative of the top. What's the derivative of x? 1 over the derivative of the bottom. So we have 1 again, minus, and remember this is really 5x to the 1/2. So when I take the derivative, it's going to be 5 halves x to the negative 1/2. And you do need to say evaluated at x equals 0. Okay, well, let's think about what that means algebraically. This is 1 over 1 minus 5 over 2 radical x. Keep evaluating at x equals 0, otherwise it's not an equivalent statement. I show that because really this is a complex fraction again. If I plug 0 in right now, I still have an undefined issue over here. So maybe what should I do? Treat it as a complex fraction again, multiply every piece by 2 radical x. So it's going to be 2 radical x on top over 2 radical x minus 5 on the bottom, evaluated x equals 0. And then finally, when I plug in 0, 2 radical 0 is 0 on top, 0 minus 5 on the bottom. What's 0 over negative 5 equal to? And that's just that situation, 0 over a number. So your limit is 0. Good? Of course it is. Okay, last example for today. Let's do the limit as x goes to 0 of radical 1 plus x minus 1 minus x over 2 all over x squared. If you'd like to try this one on your own, by all means, pause the video and give it a shot. I think it's doable. If you'd like me to go through it, here we go. Okay, plug in that 0. We're going to have radical 1, which is 1, minus 1 is 0, minus 0 over 2, top is 0, bottom's clearly 0. So this is a L'Hopital situation. Okay, derivative of this first piece, think of it as 1 plus x to the 1/2 power. So it'd be 1/2 times 1 plus x to the negative 1/2 power times the derivative of the inside, which is 1. So we'll just leave that off. The minus 1 is going to go away. What's the derivative of minus x over 2? Well, it's like 1/2 x, so it's just minus 1/2 all over 2x. What's the problem if I leave it like this? Notation, notation, notation. We got to put evaluated at x equals 0. So then plug in 0. So it'd be 1/2 times 1 to the negative 1/2. But whenever you have 1 to a power, whatever, regardless of whatever crazy power it is, it's going to be 1. So 1/2 times 1 is 1/2 minus 1/2 all over 0. 0 over 0. Well, that's annoying. What's that mean? It means we've got to do L'Hopital again. Okay, let's do it. Bring the negative 1/2 out front. Now it's negative 1/4 times 1 plus x to what power? We'll subtract 1 again. Now it's the negative 3/2. Minus 1/2 is a constant, so that's going to go all over 2. Don't forget to write evaluated at x equals 0. Okay, this is looking good. It's definitely not going to be L'Hopital again because we just have 2 on the bottom. When I plug 0 in, remember this is 1 to a power. So 1 to a power is always 1. Times negative 1/4 is negative 1/4 over 2. Complex fraction, multiply top and bottom by 4. So negative 1 over 8. Negative 1/8 is the answer. Isn't L'Hopital great? It sure is. Okay, so now you can do problem set 109. So go for it. Good luck. As always, email if you have any questions.